Hello everyone, and welcome back. Today we're going to introduce a very important concept in terms of applications, and that is called Monte Carlo simulations. Once we go through some of the theoretical background for Monte Carlo simulations, we're then going to go through an R coding demonstration of actually how to conduct a Monte Carlo simulation, because if you don't know what a Monte Carlo simulation already is, you'll realize that you cannot, at least practically, do these by hand because they require many calculations. So let's briefly go over a couple things that you probably already know so that we can sort of get some motivation as to why Monte Carlo simulations are even necessary. So let's start off with a very basic null hypothesis that you're very familiar with, and that is that the mean is equal to some numerical value. Let's call it mu0, and let's assume we're going to keep things simple and use a two-tailed alternative that mu is not equal to mu0. So we need to estimate mu with something, and we know that the expected value of x bar is equal to mu, implying that x bar is an unbiased estimator of mu, and we also have a formula for the standard error associated to this point estimate, and that's going to be equal to sigma over the square root of m. We don't usually know sigma, and hence we have to approximate it with something, and we know s squared is an unbiased estimator for sigma squared, so using s to approximate sigma, at least from that standpoint, is a good choice to have. So we would probably like to build a test statistic for this, and let's call it a mean stat, so a mean test statistic or a test statistic for the mean, and let's define it to be equal to x bar minus mu0 all divided by the standard error associated to x bar. So the main question that we seek to answer here is what distribution does this random variable have, right? Because keep in mind, x bar is a random variable, mu0 is a constant, se x bar, if we define it to be sigma over square root of n, is a constant. If we define it to be s over square root of n, that se x bar is now a random variable because s would depend on that random sample that we would select. So what type of distribution would this have? That's the important question we need to answer here. So, for example, you'd probably be like, oh, it follows a z distribution or it follows a t distribution in each of these cases. Not necessarily. So what usually causes the confusion is a misunderstanding of the central limit theorem. And it practically says the following. So as n gets arbitrarily big, the probability density function of the random variable x bar approaches a normal distribution. That is, the distribution of our mean test statistic would follow a particular normal distribution that's shifted by mu0 and it's divided by a standard error of x bar. If that's based on sigma, then that's going to be a z distribution in that particular case, which we sometimes refer to as a z distribution, and it's going to follow a t distribution with n minus 1 degrees of freedom if it happens to follow the s over square root of m. But the key point in the statement is that the distribution approaches normal. It never gets to it exactly. That's the big point, right? But usually when we see this theorem, we're like, okay, well, if n is sufficiently large, some people use 30, some people use 50, some people use even 1,000,000, but even sometimes 1,000,000 sample size is not that large depending on your population size. But usually from there, we're like, okay, well, if sigma is known, then we're going to say, okay, it's going to follow a z test statistic, in particular x bar minus mu0 all over that standard error expression. Or if sigma is unknown, then we're going to be using a t distribution, a t-stat, which is going to be equal to x bar minus mu0 all over s divided by the square root of n, since that's the standard error representation. Because we know that if x comes from a normal distribution, x bar will also follow a normal distribution, s will follow a chi distribution, and hence this t-stat will follow a t distribution. Or if sigma is known, then x bar is the only normal random variable in this picture, and hence once we standardize it, it becomes a z random variable in that particular case. But again, it never gets exactly equal to these distributions if the distribution that we're sampling from is not normal, right? But if it is coming from a normal distribution, we can use these test statistics and their associated distributions exactly with no worries, right? But if it doesn't come from a normal distribution, all we can gather from the central limit theorem is an approximation to the true distribution. But that doesn't answer the original question, what distribution does it actually come from? Most of the time, it's very complicated, or in some sense, unknown to anyone, right? So let's just state a couple things that we definitely need to realize at this stage. So if x is not normal, especially for small sample size n, like for example 5 or 47 out of 10,000 or even 500 out of 10 to the power of 8. Those are all small. 30 is nothing special about this number. Then, and the distribution of x is very different. And keep in mind, we usually don't know what this distribution looks like, right? But you can use your imagination. Maybe the distributions we're sampling from is sort of like that. Does that look normal? Probably no, right? So if that is the case, then the distribution of x bar or z stat or t stat will not at all be normal, z, or t. That is very important to understand, regardless of how large your sample size is. So, if we calculate these z stats or t stats, which are technically not associated to a z or t distribution in the practical sense, we still need something to compare them to. So, here's the main question. How to calculate critical values or p-values if we don't know the distribution of our test statistics. And that is where Monte-Carlo simulations come into the picture, because in some sense we don't know. As long as you're able to simulate the sampling process, we can always generate what is called an empirical distribution, which is a point estimate for the overall distribution, which will allow us to get point estimates for any critical value and any p-value for which we're interested in analyzing. So let's go back to our original example where we're interested in testing that the mean is equal to some particular claimed value. And let's assume that we are able to construct a test statistic based on only the sample statistics, for example, S and X bar, i.e. we can't even use Z if we had the assumptions met for that particular distribution. But let's assume that the value of this test statistic came out to be 3.26. And again, we do not necessarily know what distribution we are sampling from. Therefore, even though we are calling this a t-stat, it doesn't mean it's coming from a t distribution, or it's not going to follow a t distribution for random samples. Keep that in mind. Just because we call it a t-stat doesn't mean it will follow a t distribution. So, how does Monte Carlo simulations help us solve this issue? Because we still need to answer the question, is this sufficiently large enough to reject the null hypothesis? So, the Monte Carlo simulation process usually can be summarized into 3 steps. So let's walk through these steps one by one. So step 1. So the first thing that we need to do is select several, and when I say several, I mean like 1,000,000 plus samples, right? But in general, more the better. If you have the computational power to do 5 billion or 10 trillion, more power to you. So select several samples of size n because we need to compare it to something fair. Since we already have selected our sample of size n, we need to be comparing the test statistics of other samples of size n to sort of see if ours is large enough or if it's just large by chance, right? So this set n is the same as our sample size. So select 1 million plus samples of size n from the distribution we know our sample came from. And if we do not know what distribution that our sample came from, then you can default it to be equal to a uniform distribution, because a uniform distribution does not have any shape. Everything is equally likely as far as we know, right? So the uniform distribution, as mentioned before, is the distribution that you use when practically you don't know anything about what you're sampling from, right? So you can always default to a uniform distribution in case you do not know that it came from a t, or it came from an exponential, or it came from a log normal, or anything of the sorts, right? So select several samples of size n from a distribution, default to the uniform distribution. So that's step 1. Step 2 is to calculate our test statistic formula for all of our simulated samples. Right? So we have our test statistic that we originally started with, our 3.26, and now we're going to have 1 million plus new test statistics associated to each of those 1 million plus samples that we drew from our potentially uniform distribution. And then once you have all of your test statistics, then you're going to probably look at a histogram of all of them. Right? So that histogram could literally look like anything. For example, are you expecting it to be smooth? Probably not. But usually, if that test statistic is going to have any particular shape, it's going to have some shape that should be meaningful to what you're sampling from. Right? So in this case, we have a skewed right distribution. Maybe this is what it looks like, for example, the median of an exponential distribution or something of the sorts, right? So the horizontal axis in this particular picture is our empirical, which I'm going to abbreviate by E, test statistics. So this is the empirical test statistics for our samples, where our empirical test statistics are going to be equal to, at least for our example, x bar minus mu 0 all divided by s divided by the square root of m. Right? So that's the x bar of each of our 1 million samples. That doesn't change for any of them. That's our sample standard deviation for each of our samples, and that's the square root of n, which should be fixed for each of the samples if you've chosen them all to be the same exact sample size. Right? So we calculate our test statistics for each of our samples. Now, once we have that, now we're going to calculate our empirical critical value or our empirical p-value in order to compare to our particular test statistic. So this is the final and last step of the Monte Carlo process. So calculate the percentage of values that are in favor of the null hypothesis with strength equal to or greater than our particular test statistic that we sort of originated this problem with, right? Our 3.26 again, right? So for example, let's assume that our 3.26 is located here. Then we just need to calculate the percentage of test statistics in our empirical distribution that are bigger than it. And for example, we were working with a two-tailed test statistic, or a two-tailed alternative, so negative 3.26 would be equally bigger because everything is symmetric about 0 for our particular test statistic, because if those are equal to each other, then that means that top is equal to 0. So equality of x bar mu 0 is the ideal case of not rejecting the null hypothesis, right? So we would calculate the percentage of values that are in the left and right hand tail for this empirical distribution for this particular example, and that will be what we refer to as our empirical p-value, right? And we would compare that to our alpha value, right? Or you don't have to do everything with p-values. You can do critical values if you want. So as usual, we would choose our alpha, and then we can find the quantile. Some people also call it a percentile, or percentiles if you're working with a two-tailed test, such that alpha, or in the two-tailed case, alpha over 2 of values, because keep in mind that's a percentage, are in favor of our alternative hypothesis, and that will give you our empirical critical value, or empirical critical values, for which you would compare to our particular test statistic, and you can conclude whether to reject or fail to reject the null hypothesis based on your sample and based on the critical value and p-values associated to this Monte Carlo simulation. Because this, keep in mind, this is an empirical p-value, this is an empirical critical value. Now, obviously, if the true distribution does exist, this distribution should converge as you make the number of iterations for this Monte Carlo simulation go to infinity. But these p-values and critical values compared to their true values usually are going to be still a little bit different, but hopefully the more iterations you have, the more accurate that they are. That's pretty much what Monte Carlo simulation hopes. So those are the foundations of Monte Carlo simulations. Now let's go into R and see how we would actually code this and actually look at our particular example to sort of see how that turns out. So let's assume that we have some data set that we're actually interested in, for example, using a z-stat or a t-stat or a chi-square stat or whatever stat, but it requires normality. And you aren't exactly sure that your sample does come from a normally distributed population. So what type of test statistic would you use in order to test the claim, for example, that this random variable comes from any normal distribution? You've probably heard the Lilliefors test by this time, but if not, I'll sort of walk you through sort of what that says and how you can do that particular test in R. So what I have here is I have a numerical data set with a bunch of different vitamin profiles for a particular individual. And let's assume that we're testing, for example, that the thiamine levels are normally distributed. So for example, you could do a T-stat or a Z-stat for the claim value of the thiamine average level intake for individuals in a population. And you want to be sure that, for example, a normal distribution is approximately satisfied in terms of its assumption for this particular test. Right. So what I want to do is I just want to define that variable to be equal to the thiamine levels for my sample. And let's just sort that from least to greatest before we do anything else. So I'm going to extract the thiamine levels in milligrams from that particular sample, and that's going to give me a data set that's listed from least to greatest. So does this data set look normal to you or not? Of course that would be subjective, right? So how the Lilliefors test goes is it first off standardizes this distribution by taking the z-score of each of the values. So what we can do is we can just take each of the values, subtract the mean of those values, and divide by the standard deviation of those values, and that's going to find the z-score for each of them and store them in a particular vector. And let's actually go ahead and calculate the length of this particular vector, even though we probably know that it's already equal to 60. The next thing that we need to do is generate an artificial data set of size n that is associated to a normal distribution and compare or calculate their associated cumulative density probability values. So the domain values are going to be associated to the q-norm function. That's going to give you quantiles for standard normal distribution. And let's partition that into n plus 1 areas, which is partitioned based on n points that should be distributed associated to a normal distribution. So we can easily do that by creating a sequence from 1 to n, increment by 1, and divide each of those numbers by n plus 1, and let's just make sure that those critical values are generated from the lower tail and increasing from left to right. And then what we can do is generate the probability values from each of those, and that's going to be done with the p-norm function, and again, let's just make sure that that's associated to a lower tail. So, since our set x was least to greatest, z will also be from least to greatest, and hence f of z should be a monotonically increasing function that is bounded below by 0 and bounded above by 1, which is going to be our probability values here. And of course, keep in mind, if something doesn't necessarily look right to you, always make sure your code is exactly what you said it should be. Keep in mind that these quantiles should be generated from a lower tail, not an upper tail, and those probabilities should be also a lower tail as well. So you should have, again, as I said, a monotonically increasing function from about 0 to about 1, which our dataset now properly gives us, right? Debugging in any coding language is always the fun part. All right, so that gives us our empirical distribution. Now let us calculate the probabilities associated to our actual data set. So this is going to be our empirical cumulative density function, which is going to be denoted by fz. And then we're going to have our theoretical CDF of what they actually are associated to, which I'm going to represent by psi z. So psi z is going to be, again, p norm, but we're going to be comparing those to our actual sample values, which we stored in the vector z. Right? So that's also going to be associated to lower tail, again, is equal to true. And that's going to be our values that we're going to compare our f values to. So if we look at the numerical values for these, of course they're not the same and we don't expect them to be, but we would like them to be approximately equal to each other one by one. Both of them, of course, listed from least to greatest, if we want to have evidence to believe that our sample comes from a normally distributed population. So let's just generate a quantile plot for the actually a cumulative density function plot for these two cumulative densities, and let's make this nice, sort of like we did when we discussed distribution testing in R, in case you saw that. So let's just do a quick plot. So let's plot NZFC. Let's do a nice title for this. So this is the empirical and theoretical standard normal cumulative density functions for our data sets. And let's just give it some graphical details in terms of the size and our shape. So that is our first distribution, and we of course need to compare it to something. Let's compare it. Let's actually draw lines on those curves. Let's do lines NZ, FZ, color. Let's do steel blue. Let's do a line width of 2. Right, so there's our first set. And then we're going to be plotting our theoretical points, which is going to be NZ, and then psi z, and then PCH equals 1, and CEX equals 0.8. So that's our point values, and those should match exactly if we have exact evidence to believe it comes from a standard normal distribution, but of course slight variation is expected. And let's color those with some lines. Let's do NZ, psi z, and let's do a color equal to, let's do violet red. Let's do violet red, LWD is equal to 2, and that gives that particular curve. So if we have ideal evidence to believe it comes from a standard normal distribution, or any distribution rather, then those pink and blue lines should line up practically always. So the Lilliefors test statistic is going to be equal to the maximum difference between these two distributions in terms of absolute value. So it's going to be the maximum absolute value between psi z and fc. Psi z and fc. So in this case, we're going to have a Lilliefors test statistic of 0.1. 1, 2. And obviously you can do, for example, a Kramer von Mises or an Anderson-Darling alternative for the Lilliefors stat, but let's just keep things simple for now. So, if you know anything about the Lilliefors test statistic, you should know that it's bounded below by 0, bounded above by 1, and if it's equal to 0, then that's ideal evidence to believe that these curves match practically always, right? But 0.12 is not equal to 0, it's definitely bigger than 0, so we need to answer the question, is this test statistic too large? But we don't have a critical value to compare it to, and we probably don't know what the Lilliefors distribution or the L distribution looks like in order to generate it, right? So this is where Monte Carlo simulation enters the picture of where we would actually want to empirically estimate what that Lilliefors distribution actually looks like. So the first thing that we probably would want to do in order to, maybe have some reproducibility things for our Monte Carlo simulation is to set a seed in R so that practically everyone who wants to follow along with us will get practically the same exact answers as I. So what I want to do is just set a seed. Let's just do 1, 2, 3, 2, 1. You can choose whatever number you want, but if you want the same answers as me that you see, then you should be using the same exact seed as me. So let's define the number of iterations that we want to do. Let's just do 10,000 just to keep things short. But of course, if your computer can handle more, it's going to take longer. But you can always increase that a little bit later in case you really want to. Right. So what we want to do is we want to generate a bunch of Lilliefors test statistics for our simulation, and we want to store all of them into a vector. So this is going to be called a simulation LI stats for the simulated LI test statistics. Right now we haven't sampled anyone, so right now it's going to be a blank vector, so we're just allocating the place where we're going to be saving them, and we're going to be saving them into sim LI stat. So we're going to sample and sample and sample 10,000 times, so obviously a for loop is appropriate here. So we're going to sample in the range 1 to the number of iterations that we want to do, and open close brace for the body of our for loop. All right, so next we're going to sample, so I'm going to call it SimSam for a simulated sample, and we're going to sort a randomly distributed data set. Because we're sampling, we know that we're sampling from a normal distribution, or we're hoping it is. So if it happens to be from a normal distribution, how large is too large by chance, and how not large is large? Actually, we can use a uniform distribution just to see what that looks like, just to see what it may, actually, no. Since we're doing a Lilliefors test statistic, a normal is more appropriate. And also, I'll let you think about why that is in a moment. So we're going to sample of size n. Our mean is going to be equal to 0, and our standard deviation is going to be 1. Let's not run this until we have the entire for loop built though. And then we're going to calculate our standardized version of that sample, because this, even though we're sampling from this particular distribution, it will not exactly have a mean of 0 and a standard deviation 1. It's just a bunch of random numbers from that place. So we need to standardize it. So it's going to be SimSam minus the mean of SimSam, all divided by the standard deviation of SimSam. And then we're going to calculate the associated distribution for the CDF. So that's going to be P norm of SimZ, and then again, lower tail is equal to true, and then the simulated LI stat, because the empirical distribution is still going to be the same exact size, so we don't need to change F. So the simulated is going to be equal to, we're going to take our LI stat, which is a vector, and we're going to append the value, the maximum value of the absolute value of sim size z minus fc, right? And that is our for loop. So if that is ran and written correctly, we can just give that a run. You'll see a little plus sign there if it takes a pretty while, but mine is practically done, so no worries there. So once we have that done, now we can generate our histogram to sort of get a sense of what this test statistic distribution looks like. So we can do a histogram of our simulated Lilliefors test statistics, and let's do, for example, 60 breaks, and let's give it a color. Let's do khaki. Right. So this is going to be our distribution, and it should be breaks, not break. right? And that's going to be our histogram. And keep in mind, all these values should be between 0 and 1. Notice that if we get any test statistics that are bigger than 0.16, that's definitely going to be a red flag because out of our 10,000 samples, none of them was able to get a test statistic bigger than that. Keep in mind, our test statistic was equal to, what was it, 0.12. That's definitely in the upper tail, but if you choose a particular alpha value, is that going to be significantly large compared to this Monte Carlo simulation? All right, so we practically have everything we need. Now we just need to calculate our empirical p-value and our empirical test statistic in order to conclude. Right? So empirical p-value is going to be equal to the following. So I'm going to call it p-value E, and it's going to be the percentage of values that are more in favor of our null hypothesis compared to our test statistic that we were able to get. So we're just going to take the average of all of the values, so it's going to be mean of sim li stat that are bigger than li stat. And if you have, for example, a two-tailed test, you would have to do, for example, the mean of this and or the mean of this or the mean of that. So you would have to do a two-part function on the interior of that code. Because keep in mind, this is just a binary statement. It's just a bunch of zeros and ones. Either it is bigger than that or it's not. So it's just adding up all of those ones and dividing by the total number of iterations, which in this case is 10,000. And that gives you the percentage of values in this particular vector that satisfy this particular comparison, which is why we're using the mean function in that particular case. So that is going to be our empirical p-value, which in this case is 0.0098, which is relatively small, right? So if it's relatively small, for example, it's definitely less than 5%, if you like that number, that means our test statistic is way too high, or our difference between our CDFs is way too large, which means we have evidence to believe that our distribution did not come from a normal distribution. Right, so we can also calculate our empirical test statistic. Right, so we can call it, for example, Li crit, but it's not an Li crit because it's an empirical one. And we can use the quantile function to calculate, for example, the upper 95th percentile or the upper 5th percentile, which is the lower 95th percentile. Everything in quantile world is based on the lower percentile. So we're going to be looking at our sim Li stat vector. And the percentile we want is 95, or 1 minus the alpha vector, or alpha value. So let's assume that our alpha is equal to 0.05, and let's actually define that. Let's just define it to be 0.05, for example. And we want the upper tail, so it's going to be 1 minus our alpha value, and that's going to give us our critical value, which is given to be there. So we compare our empirical p-value to our chosen alpha value, 5%, or we can compare our test statistic to the critical value. You'll get the same conclusion. So our test statistic was 0.12. Is that sufficiently large? Well, as long as it's greater than our empirical critical value, we will reject the null hypothesis based upon our observations, which it indeed is. Right? So that's how you calculate empirical critical values and empirical p-values from a Monte Carlo simulation. And this is the approximate distribution for a Lilliefors test statistic based upon a sample of size n. Obviously, if you change your sample size of size n, this distribution will skew a little bit more in one or both directions, which I'll let you experiment in case you're curious. But those are the main principles associated to Monte Carlo simulations and also how you can implement this in R. I hope you enjoyed this video and I'll see you in the next one. Take care.